Hello everyone. As we mentioned in our last class, we have already completed two basic parts of our design project, horizontal alignment and vertical alignment. Now we have only one final, third part left to the complete, the so-called cross-section. So let's begin. The cross-section depends on the location where we'll be creating it on our railway line. The basis for designing a cross-section is to create a so-called typical cross-section or a normal cross-section. As you might guess, the positioning relative to the railway line will define the conditions under which we will build our railway line. Generally, this will come down to locating the railway line either on an embankment or in a cutting, and these conditions will be most important for us. But before we moved on to that, you can see how different conditions look on the map. The situation at the green dot, where the embankment is located, will look quite different from the blue dot, where there will be a cutting. So basically, we have two different localizations, the embankments and the cuttings, the excavations one. Before we proceed to design, let's discuss what a cross-section actually is. According to a definition, a cross-section is two-dimensional vertical section perpendicular to our railway line along its entire length, which illustrates all structural elements of our railway line at a specific point. Here, you can see a segment of a railway line on a slight embankment. You can see that what is designed is shown in red. We have a certain route, a railway line, located in a specific characteristic place. The cross-section provides us with complete information about all elements located in the horizontal and vertical alignment. Of course, the most important are rails, railway sleepers, and ballasts. Additionally, we have information about the protective layer and the subgrade. We can also read information about the drainage system and see under what conditions our railway line exists, whether our line is on an embankment or in a cutting. Also important is the so-called structure gauge connected with engineered structures, which we haven't discussed yet and which is related to railway vehicles moving on our railway line. But before we get to structure gauge, you can see what a typical cross-section looks like with the most important elements marked. Of course, you already know the surface and the structure elements perfectly. Number 1 indicates the ballasts. Number 2 indicates the protective layer. Number 3 is the so-called upper surface layer, while numbers 4 and 5 are layers related to the subgrade. The subgrade itself, and either the cutting or the embankment. Element number 6 is the longitudinal drainage of the track. This can be done in the form of surface ditches or deep drainage. Moving on, we can return to our structure gauge. In principle, our EN standards does not reference typical construction standard for our structural gauge. However, technical specifications for interoperability show us several specific solutions. Here we have 4 typical gauges: GC, GB, GA, and G1, which are suitable for both passenger and freight traffic. These gauges are permanently linked to the type of rolling stock that will be moved on our railway lines. You already know the appropriate traffic codes and related to the maximum speed of our vehicles and the load carried by railways vehicles. For this reason, different conditions need to be considered for these vehicles, and the references clearance will differ slightly from each other. However, as a rule, Most of them have very similar dimensions that actually differ only in nuances. In the first three drawings, you can see the upper gauge image for these four basic gauges. In the bottom drawing, you have the lower gauge image, which of course needs to be symmetrically reflected to have a complete gauge picture. Understanding structure gauge is important because it defines what structures and infrastructure elements can accompany us with, and what space must remain free so that our vehicles with given geometric parameters can safely move on our railway line. The most basic element of our cross-sections from which we begin the discussion is of course our railway surface and its elements. You already know the basic elements are railway rails, sleepers, fastenings, ballast, and subgrade. And the designing a cross-section is actually related to the selection of individual structural elements. Hence, it is necessary to understand how this is done for individual railway infrastructure managers around the world. Just as there are many railway managers, there are many different specific requirements for each railway system in individual countries. Here, for example, I cite some of the better-known railway infrastructure managers in the world, actually in Europe, and you have some freedom regarding which manager's regulations you will use information from. For order, I will mention just a few of them, reading from the top left. Germany and Deutsche Bahn, then Switzerland and Swiss Federal Railways, next Italy and Rete Ferrovia Italiana, then Spain and Administrador de Infraestructuras Ferrovias, followed by Belgium and Infrabel, then France and Société Nationale des Chemises de Chauffeurs François, and finally the Polish railway infrastructure manager, PKP Polskie Linie Kolejowe. As I have told you, you can choose any infrastructure manager and based on their internal regulations, select all structural elements for your railway line. I will present the project to you based on the Polish regulations, of course. Designing railway infrastructure and cross-sections according to the standards of PKP Polskie Linie Kolejowe comes down to deciphering a certain large table. I won't explain all the details here, but we can quickly simplify this table to a simple table for which the reference point is one key technical operational parameter, namely the maximum speed. This table is actually related to the threshold value of the maximum speed of 120 km per hour. From this threshold, we can actually define the individual structural elements of our railway surface. And then, if our maximum speed is below this limit, we will most likely have 49 E1 railway rails, sleepers in the form of PS83 or wooden ones, rail fasteners will be related to the sleepers, and the rails used and the ballast will be crushed stone with a fraction of 31.550 class A. In the second case, if our maximum speed will be more than 120 km per hour, we will actually change two elements, the rails and the sleepers. Accordingly, the rails will have 60 E1 profile, while the sleepers will be PS94 sleepers. The other elements will remain unchanged. After agreeing on the surface elements, we must design the geometric dimensions of the subgrade. Here we need to determine several elements. The first is the minimum thickness of ballast under the sleeper. This is defined simply and it sits at a minimum of 35 cm measured from the bottom of the sleeper. The second important length is the agreement on the width of the ballast measured from the face of the slipper. Here, depending on whether our maximum speed is less than 200 kilometers per hour or greater than or equal to 200 kilometers per hour, we have two different values. If the threshold value is greater than or equal to 200 kilometers per hour, the width of the ballast measured from the face of the slipper is 50 centimeters. Otherwise, the width is only 45 centimeters. In order to complete our subgrade and cross-section design, we need to determine the three key parameters. The first is the width of the so-called track bench, which in all cases should be a minimum of 60 centimeters. This parameter is denoted by the letter E in the drawing. The second parameter we need to determine is the minimum depth of our drainage measured from the track level. This value is 50 centimeters and is denoted by the letter I in the drawing. The last element we need to design is the transverse slope of our embankment or cutting, which of course depends on the type of soil from which the subgrade is built. However, we can assume it as a slope with a ratio of 1 to 1.5. We also need to establish the range of the transverse slope of the track, which, as you can see in the drawing, is specified in the range from 3% to 5%. Taking into account all this information that we use to determine typical values, we can design a so-called normal cross-section. As you can see in this drawing, we have presented a typical cross-section for the construction of a railway line in accordance with the standard of Polish railway lines, PKP Polskie Linie Kolejowe. We have shown both the cutting and the embankment on which our railway line is located. This drawing is not particularly completed, but it will provide us with the basis for designing specific cross-sections at points specified by me in our design exercise. And it is from this that you will relate the solution for your railway line, designing the surroundings at each specific transverse point. And the designing these specific transverse points will be the third and the final drawing that I will require for passing the design exercise. As you can see on the example slide, a railway line can exist under various conditions. Here, the green line represents the terrain to which you will have to relate your designed railway line, and the situations you observe will be different. However, as a rule, the typical cross-section will be used at each point. Various situations may appear in your projects. Some of them will be deep cuttings, as you can see in these drawings. Sometimes you will also have relatively shallow cuttings. However, regardless of the situation, the starting point once again is, of course, the typical cross-section. You can also perform design exercise in different ways. Depending on the software used, skills, and project detail, your cross-sections may look different. However, it is important that it contains all the essential elements that allow for the identification of the railway line structure at a specific location. You must also remember that sometimes the railway line will be on a straight section, as shown in this slide, or a circular curve section. If a circular curve appears, remember that you will most likely have a super elevation. In this case, you should appropriately mark the super elevation, the count, and the profile the individual track layers so that they are adapted to the assumed super elevations, the count. And that's really all the information that will be sufficient for you to create a cross section. Of course, the locations where you will create the cross sections will be indicated by me. To this, and for me to determine the cross section, you must first complete the site plan as the vertical alignment and the horizontal alignment of the railway line. Only then, on the accepted railway line, I will mark one location where you will create the cross section. And I think that's all you should know. So thank you very much. I look forward to hearing from you and seeing for you. And if any questions arise, I will be happy to answer them. Thank you and goodbye.